question for you guys. But I'll go with you.
All right. Okay, there we go. Right. So everyone, so thank you all for coming. So we're going to be talking about Markov chains and how it's used in autocomplete. So the agenda for today, we're going to talk about the basic theory of Markov chains to get an idea what that is. We're going to see how its applications, including autocomplete, and then we're going to do some fun projects with that. And there might be a small aside at the end. So let's begin. So what are Markov chains? So basically you have states and you have arrows. So given each state, if you start at one state, you could go, there's probably a staying in one state or going to a different state. So let's say you're at E. You have a, I don't know what the number says behind that. You have a 30% chance of going back to E from E and a 7% chance of going from E to A. And then the same applies for A. Notice how all the weights of the arrows coming out of the state, it sums up to 1 because you go 6% going back to A, 30% going back to E, and then where do the 10% go? What do you do? So you can show a little, let me show you a little demo here. Talk about this. Oh, this Markov state. So you see by random chance, it switches between states. So sometimes it stays, sometimes it switches. And you can change the probability of how likely it is in each state. So let's say once you go to A, you're stuck at A forever. We can increase this probability such that it will be 100% always going back to A. But what if you hate going to A? What if A is such a bad place you want to leave it immediately? Then we can change the probability of every time you go to A, you'll immediately go back to B. And if you want it, and everything between, so those are the two extremes. And in between, you sometimes stay at A, sometimes stay at B. It's random chance. And you can do this for B too. You can change the probabilities of B to always leave B or always stay at B. Let's go back. Okay. So Markov chain is memoryless. It does not remember which state it has been. So once you leave A, it doesn't remember that it has been in A before. So a transition matrix is a matrix that lists all the probabilities of going from one state to another. So the rows represent the starting state. So let's say, and then the columns represent the ending state. So let's look at the top example. So the probability, the transition matrix P. So let's say you want to go from state A to state C. What is the probability that you go from A to C? So let's look at the row A, and then we look at column C. So A is the first row, and then column C, the ending state, is the last row. So you have a 90% chance, given that you start from A, you go to C. So do you guys want to try something out? So what if I'm starting from B? How likely am I to go to C? Yes.
0.9 or 90%.
All right, good. What if I want to go from C and stay at C?
0%. Yeah. 0. There's no way of staying at C after you get this.
Yeah. So that's the basic idea of transistor matrices. So it's given that, but every row, the sum of the probabilities of each row add up to 1, because given the state you're starting at, you have to go somewhere. You either stay or you go somewhere else. You can't, there's no other option. So the probabilities of either staying or going to a different state adds up to 1. So let's say you want to calculate the probability of being at the state A. So have you guys heard of the chain rule of probability? Okay, I assume not. So what it says that given the probability of of you in the current state, how likely are you to be at A in the first place? And then you multiply that by the probability of going from A to B, or from A to wherever you want. And that's probably of getting to that whatever's ending state. So this last term, P of S state T1 given as T, you find that from the transition matrix. So it's just saying, okay, given that you're in this state, how likely are you to go to the next state? So you start at the state, how likely are you to get to this current state, and then how likely it is for you to go from that current state to your next state, and that'll be your probability of the current state, of the next state. So, however, this only handles one path. So what if you want to find the probability of like B, right? Let's go back. So B here, it doesn't have A, or it doesn't have just like A or C. You can get there from both A and C. But this equation only considers one path. How do you think we're going to consider all these paths? Not necessarily. So let's say you want to be at B. So you can either start from A, or you can either start from C, or you can start from B. And you have the probabilities of going from A to B, and then from C to B, and then from B to B. So what do you do with those pieces to find the probability of being in B in the next state?
You multiply probabilities together.
Like something called that could be more than
I think it goes with some part. Probably you multiply the probabilities. It's like it's like continuous events. That's what you multiply. So if you want to have like remember like once you multiply or add in like probability. So when do you usually multiply it when you calculate probability?
When you do it in sequence.
You don't think it's sequence.
When it's independent of the other.
Well, when you're summing.
When it's like a or, I guess, statement. So if there are two different ways of getting there, you add probabilities.
All right. So now, so those are like two crucial hints. So how do you?
Well, I guess you just sum up the probabilities of each different way to get there.
That's exactly correct.
I know it.
So the probability of ending up at a certain state is the sum of all the probabilities of any potential current state. So the probability of going from A to B, and then from B to B to C to B, whatever state, all the states that lead to B, that's the total probability. So, and we can represent this using a matrix and vector multiplication. So this left hand of the equation is the probabilities of it being the next state. So the probabilities of each of these being the ending state. And then the first this is just like the starting probabilities. Like you're equally likely to be at a certain state initially, but then once you transition, this is the probability at, let's think of this as t equals 0. So this is your initial probabilities, and then you transition at once. And then these are the probabilities of being in each of those states at t equals 1. Do you have any questions? Or you just lost in general? Or you got this? All right. So what if you want to go to 2 states? So t equals 2, t equals 3, t equals 10, t equals 100, t equals a million. So what you could do is you find the probability of going from one state to the next, from T0 to T1, and then you use the same process, calculate again from T1 to T2, and then using the same process again, T2 to T3, and you just keep individually multiplying the transition matrix every time. You're just doing it recursively. So you're plugging in whatever you had the answer from the last iteration and putting it into the equation for the current iteration. But you're multiplying it by the transition matrix anyways. So because each transition, you multiply by the transition matrix. So let's say, so we could do the second approach where you just like take the power matrix power of the transition matrix. So let's say you want to see the probabilities after 100 moves, right? So what you can do is take the initial probabilities of being in the state, and then you take t to the 100th power. Then you multiply those two, and you get the probabilities of being in each of those states after 100 moves. You get this so far? All right. So now, eventually, if you keep doing more moves, it's gonna converge at some step probability. So after like a million, a trillion states, the probabilities of being at each of those states will stay the same. So it will like very, very little. So as you keep making transitions, the probabilities will converge to a value. And this is more like a fun fact, but that final converged probability is the eigenvector of T. So how many of you guys have taken linear algebra? Okay, so for those who haven't taken linear algebra, the eigenvector is some value such that, I don't want to get too technical with the eigenvector value, but essentially you multiply the transition matrix times P, the final converged probabilities, it will be equal to any constant times P. And this is important because if you can find the eigenvector of the transition matrix, you don't need to like iterate many times to find out what the final probability distribution is at the end. So this is just more like a shortcut to see where all the probabilities and likeliness of being at what certain state converges to. So hidden Markov chains are different such that sometimes you can't just observe a state itself. So you can't tell if, let's say for this hypothetical scenario, you don't know if the market is up or the market is down. You're like, you come outside having a next day, and then you see something sad. And then the first thing you probably think is, is the market up or is the market down? So based on like the expression of the person's, based on the person's emotion at that time, you can see if the market is like up or down. So what the hidden Markov chain does is, given like an observation or like resulting variable or what you saw, you can like predict like what's the current state we are in, even though you're not actually looking at the state itself. Right, so now we can go to different applications of Markov chains. Right, so there are way too many applications, but I put like the most popular or pretty interesting 3 on here. So the first one is PageRank. So without looking at the slide, what do you think PageRank is? Mm-hmm. Exactly. So you're ranking the pages. Wow. Okay, so how Google search algorithm works is that it has a web surfer that randomly just goes between each state. The state in this case is a web page, and each web page has links to different web pages, and sometimes it can link to itself. So what the surfer does, it just randomly traverses each page through links, and then eventually they'll all converge to that final probability P, as I mentioned earlier, and then based on that probability P, then it ranks the pages based on like the higher probabilities. So what this does, it makes sure that the higher ranked pages are the ones that are endorsed by other higher ranked pages. Oh yeah, and the damping factor is like in case there's like a cycle or like there's a separate component, it just like randomly teleports the bot. So let's say G, A, and D are not connected to the rest of these. If it just randomly dropped on G, it's just gonna go to A, G, C, A, G, C, A, G, C. But the damping factor teleports them to B, F, E, so they have a fair chance of also being equally ranked. So speech recognition is also a very interesting use of hidden Markov models. So let's say you're trying to like doll, for example. You can't observe sound, or computers don't really observe sound. They observe like the wavelengths or like the frequencies of each sound. So when I say duh, it observes the wavelengths, but it's not too sure if it's a D or T or a what other word makes a duh sound? So like V. So what it does is chooses the most probable like letter that makes that sound and adds it to the word. And then it does that for the next letter. It does that for the next letter. And if it makes sense that the previous letter goes with the current letter, so let's say D-O, that makes sense, right? But if I put DG, that does not make sense. So repeating that process for like each character, like finding the most probable sound, and then finding if it matches with the previous character. And then it builds up from like characters to build words, and then each word and its sentences. So it's slowly building up each time. So let's say if it's like, if you hear DG sound, so D, and then it hears a G sound, it's most probable, and DG doesn't make sense, right? So you don't see many words with D and G at the very start of the word. So what it does is says, oh, that's not likely for D to be followed by a G. So it reverts back and chooses like the next most probable like letter and see if it makes more sense to be preceded to follow D. And then the one you've been waiting for, autocomplete. So most of you guys know how autocomplete works. You type in a word or a phrase, and then autocomplete just like completes the word for you. So let's say you type in "thank you very." Most likely, it's going to predict "much" as the next word because you usually put "thank you very much" right after instead of like "thank you very Apple." So based on like the data, and each word is a different state you can go to. So thank you, thank goes to you, and then you goes to very. That makes more sense. And then you go, and then very is much. It's like more likely to go from very to much than from very to any other word. So each word is a different state, and each like sequence of words is a different transition. So going from thank you to thank to you is a transition that has a probabilistic weight pretty next to it. And you've seen autocomplete everywhere, so you know it's used in search and texting. So let's do some.
Autocomplete is a feature within Google Search designed to make it faster to complete searches you're beginning to type. We created it to help save people time, which it definitely does. On average, autocomplete reduces typing by about 25%. How it works at a very basic level is by looking at what you're starting to type in the search bar, sorting through trillions of past Google searches to find ones that include the letters you just typed, then displaying some of the most common ones. So what you see in autocomplete are predictions based on lots of data about how people search. That's why the first queries you typically see are your own past searches, because data tell us users tend to repeat them. Those predictions are indicated by a clock icon, and you can delete them right in the search bar, or you can visit your Google account page. Another thing to know is that a common query in one part of the world may not be so common in another. That's why autocomplete considers location, as well as the language being used when displaying predictions. Autocomplete also takes into account what searches have been trending, which is why queries related to the news or recent events may move up the list of predictions when relevant. The last thing autocomplete factors in is what you won't see. Predictions identified as inappropriate, harmful, or otherwise against our policies. We don't stop anyone from searching for whatever they want. We've simply designed policies so people won't be unintentionally surprised, shocked, or otherwise shown unhelpful predictions in autocomplete. Because autocomplete has always been about getting you to what you're really looking for quicker. And with billions of searches being completed every day, our predictions will keep getting better, getting you to results even faster.
All right, so after hearing me ramble for such a long time, we can start on the project. So have you guys downloaded the repository? It should be from your from the email sent out.
Anyone who is still voting it right now? Or it doesn't have to go on. Cool. If there's no objections, then we'll move on.
Yeah, I think that was just so we could get let's start it. So I'm just gonna click here. We're gonna pull up. You're gonna be doing most of your work with the Jupyter notebook. So let me know if everyone's ready. So just give a thumbs up or so ready to get started? All right, so once you get the repository cloned, what you want to do is type pip install R and requirements txt in your terminal. This should download all the required libraries you will need or packages you need. We're good. All right. So to make sure everything has been installed properly, run this code block. Make sure no errors pop up.
You guys do all your projects in Python?
Usually, yeah. It depends on the workshop. I have no
I don't
idea.
think so. Yeah.
So now to make sure you're at the right place when you're like changing files, run this block, and this should say it should end with Shakespeare generator. So that'll be your current directory.
Yeah. To be fair, if you don't have your laptop, it's kind of hard.
It's kind of hard to follow along, yeah. If you want to do that at home, you can still download it, do it at home.
Yeah.
So now let's see if we have our data. would you look at that? We have no data. Oh no. Well, I guess the workshop's over then, huh? We have no data.
And there's so many people who are gonna just go home and be handed. It's very troubling.
Oh wait, there's something called web scraping. So this may not be your usual AI sort of lesson, but collecting data is pretty important, like in general. So let's go over how to collect data. Okay. So what the two libraries we'll be using in this case is Beautiful Soup and Request. So who knows at least one of these libraries? All right, so which one do you know? Beautiful Soup. Okay, so what do you think Request does? Makes the HTTP request. And then Beautiful Soup, it's not implied by the name, so let me go to the next slide. So yes, Request allows you to send HTTPS requests. And then Beautiful Soup, it takes raw HTML like string or like format, and it makes it more clean and easy to like get data from. So yes, that's actually the first page. That's the first image you see when you go to the Beautiful Soup documentation. So you only need 5 functions. So I know there's a lot of text, but so I'll give you a minute to like look at it, and then I can answer any like clarification questions about them. So any function or like method that confuses you so far? Okay. So now we can just go on the application. So how to apply these, because so first you have to go to scraper.py, and then you can start working on the scraping. So what we're going to scrape from is this link here from shakespeare.mit.edu. So I can't click on this link for some reason. There we go. And then you can Control Shift C on here, or like however you open up HTML. There you go. And now you see all this HTML code on the right here. So each of these are different tags. So each of these like brackets are like different tags of or like elements of the HTML file, just too many HTTPs. Then each of them have attributes. So block code is the name of the type of tag here. So this is referring to the highlighted part. If you open, you see there's an image tag, and it has an attribute of source. So the source is shake.jit. So what we want to do is get these links because these contain the text we want. So let's find where each of this corresponds, and this is an A tag. A tag, and the link we want is href. If I click on this here, there we go. If we click on this link, it just gives more links. And then if we click the entire play, it gives all the play, it gives all the text we want. So we want to get the first part of this href from the main page. And then based on the first part, we can build a link, shakespeare.mit.edu / and then the first part of the href we got it, and then follow the HTML, which gets the full text. So we're going to walk through how to do this. So it shouldn't take too long. So first of all, we want to get the page in the first place. So what we're going to do is get a response, and then request dot get, and then the link. So our link here. Now we want to get the clean soup, because right now the response has dirty soup. Or at least the content does. So what we're gonna do, we're gonna make a beautiful soup object of the response content, and then it's HTML parser. Yep. So now we retrieved. Now that we got the clean content, we want to extract all the links that we want. So do you remember which function extracts all like the, what do you think is gonna, let me pull up the functions again. Here. So all links are under A tags. So what do you think will get the tags we need to get the links? And the tag type is A, that's correct. So find all, and then the tag will be A. But since we don't need all the links, we can just take a subset of it. Right, so now let's go back. How are you going to get the href, the actual link we need? Because you're getting all the tags, but you only want one attribute of the tag. Yeah. So now we could just do link.get, and then the attribute, which is href. And since we only want the first part here, merchant, and not the whole thing, we'll just split it by the slash and take the first element. Right, so that one function done. So now walk me through how to work on the rest of this. So how did we get the soup? Okay, so we have our link here. Let's see our example link. So our original link, shakespeare.mit.edu / the part we took from the first function, and then follow the HTML. So what we're going to do is take link, concatenate that with each L. So whatever results from this, all these scraped links is a list of this middle portion of the link we want. So for each link, take the original link and then go to that sublink, then follow the HTML. There you go. You can also use that, but I'm too lazy to do it right now. Okay, so then we repeat the same process from up here. So response, I already had a set response So response, so request dot get link, and you get this soup. Very interesting. Okay. Now we got the soup, and all the text are in. Oh wait, wrong. There we go. All of this, they're in block quotes. You want to get the text from every block quote. So what do you think we're going to put here? So now we have our blocks. Now we want to get the text from the blocks. So for every block in where we found, we want to write the text. So to write, you do F, as here, write, and then how to get all the text from a tag. So b dot get text. So and remove the pass, and it should be done. Hopefully. Okay, so now we can. Has everyone caught up so far? So what we can do is then let's see if we collect our data. Look at that. Did I scrape the wrong thing? Okay, wait. Oh, I got the wrong link. Let's try that again. And hopefully you get the actual correct content this time. Yeah, it's a lot of links. It's a lot of data too, so you can choose whatever subset of data you want. Don't run all 37 though. It's gonna be too much for your memory if you're gonna make this for the rest of the workshop. And now we have their text. All right. So we can go back to our library and see if there's any data now. And look at that. We have data. Right. So has everyone gotten this point yet? Where we got all the data? Any questions? Okay. So now a lot of this is you try to do yourself. So I'll give you around, how much time do we have left? 15 minutes. I'll give you around like, I'll give you 10 minutes. And then I'll briefly go over, I won't code it, but I'll upload the solutions up later. So I'll give you 10 minutes, try work on from X2 to X4. And then if you need help, I'll be walking around helping you. And then we can go to Act 5 where we just, actually I don't agree with Act 5. But just see how you would do.
Oh.
We can represent later. Turn off the thing.
There's an offer. Yeah, you just turn on.
That's it.
No, I think it's on the,
Oh, there's one right here.
that's the,
Not one.
Or if you just want to turn this on, you can either hear you. Or it doesn't turn it off, or you can put a display off. If you turn the picture.
Every single user word.
Okay, so technically the workshop is supposed to be over. We went 5-6 minutes above, but if you want to check your answers, all the answers are here. You're going to do it on your own time. If not, you can just stay here. If you have time afterwards, I think we can stay here, right?
Yeah, we have a room until 7.
You have a room around like 7:20, so you're going to stay here a bit longer and continue working. It's fine. Then if you want to leave, then if you leave, thank you for attending this workshop. It was a bit longer than anticipated. So feel free to continue working this at home when you have time.